come to example 3 of this specific heat section, right? It says 1.2 kilograms of aluminum at 90 degrees Celsius is placed inside a glass beaker of 200 grams containing 400 grams of water at 50 Celsius. So we're going to assume that the glass beaker is also at 50 Celsius and then the water is also at 50 Celsius. Also 4 grams of ice cube at -5 Celsius is placed into the beaker, right? What is the final temperature of the mixture? So we have here kind of a quick picture. You have the water at initial temperature of 50. You have the glass at also initial temperature of 50. And then you're putting aluminum, okay? That's initial temperature of 90 Celsius, right? And then you have ice cube, initial temperature of -5 Celsius. So you're putting some hot substance into the water that's going to tend to increase the temperature of the water, right? And then you're putting a cold substance, -5 Celsius, into the water. That's going to decrease the temperature of the water, right? So what's the final temperature going to be? Well, maybe the final temperature is going to be below 50, right? Because since the aluminum's specific heat tends to be very low, the aluminum's temperature changes a lot. So the aluminum's temperature might go from all the way from 90 to maybe, let's say, 55, right? Goes all the way down to 55, and then the water's temperature goes from 50 to 55, right? But then the cube, you're going to have to heat up the ice cube, you're going to have to melt the ice cube, so the ice will take away a lot of heat from the system. So I'm going to guess that the final temperature is going to be below 50. Let's guess that the final temperature is below 50, so then what happens? Then we can say the mass of the beaker was 200 grams, right? The specific heat of the beaker, the specific heat of glass is 0.2 calories per gram Celsius. So this one is in grams. So in this problem, I'm going to keep the units of the specific heat in calories per gram Celsius, and then I'm not going to be converting the grams to kilograms, right? This one we don't really have to convert to kilograms because we're not dealing with joules in this problem. We can keep everything in calories. As long as we're consistent, they will all cancel out. So then this is going to be 50 minus the final temperature, right? Since I'm assuming the final temperature is below 50, so let's say the final temperature is something like 30. 50 minus 30 gives you 20, so that gives you a positive number. So I want to do it so that all of these guys are positive numbers. The heat lost by beaker plus another positive number plus another positive number, and then equals a positive number, right? So then I add to this the heat lost by the water, 400 grams. The specific heat of water, 1 calorie per gram Celsius. And then the change in temperature, 50 minus T final, right? Plus the mass of the aluminum, right? The 1.2 kilogram, right? This one I'm going to convert to grams so that I stay consistent. So that's going to be 1,200 grams, right? And then the specific heat of aluminum is going to be 0.215 calories per gram Celsius. So again, gram cancel, gram cancel, right? And then the change in temperature of the aluminum is going to be 90 all the way down to whatever the final temperature is, right? 90 minus TF. Okay, so then that's going to equal to the heat gained by the ice. So I'm going to have to raise the temperature of the ice to 0 Celsius. 4 times 0.5 is 2, times 5 is 10. So it takes 10 calories of heat to raise the temperature of that ice cube to all the way to 0. Then we add to that how much heat it takes to melt that ice, right? So we're going to be multiplying 4 grams of ice times the heat of fusion of ice in calories per gram. So that's going to be 79.6 calories per gram. So gram and gram will cancel. So you see everything is calorie, 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 and then calorie and calorie. So if everything is calories, they will all cancel out, right? Plus, after the ice melts, we're going to have to raise its temperature from 0 to whatever final temperature of the mixture, right? So then we have here 4 grams, and then since when the ice melts, it turns into liquid water, right? Its specific heat becomes the same as the liquid water specific heat, 1 calorie per gram per Celsius. So we have here 1 calorie per gram Celsius, gram cancel, and then what's the change in temperature? T final minus 0, right? T final minus 0, since the melting point of the ice is 0, and then therefore T final minus 0 just gives you T final, right? When we simplify that, let's see what we get. We get 440, 50 minus TF, plus 258, 90 minus TF, and then combine 10 plus this 328.4 plus 4 TF. Right? After that, it's pretty much algebra. You can combine 22,000 plus 23,000 and then bring the 328.4 to the left by subtracting it. We get 44,891.6 is equal to, and then we take the 440 and the 258 and we take it to the right side and we add it to 4 and we get 702 TF, and then TF is going to equal 63.948. 63.94, we can say 63.95 Celsius, right? Now notice what happened. The final temperature came out above 50. Oh, what does that mean? That means our assumption was wrong. The heat was not lost by the water, and heat was not lost by the beaker. It was only lost by the aluminum, right? The initial temperature of the aluminum was 90, so the 90 went down to some temperature, right? But actually the water is going to gain heat, the beaker is going to gain heat, and the ice is going to gain heat. The only object in this scenario that's going to lose heat is the aluminum. Let's reshuffle the equation and see if we get the same answer or we get a different answer. So we can say the heat gained by the ice, which is 10 plus, then we're going to have to melt the ice, which is going to be 318.4, plus we're going to have to heat the ice, which is 4 times TF. The heat gained by the beaker is going to be the 40 times the final temperature minus 50, right? This time we're exchanging the places of the TF and the 50. Instead of 50 minus TF, we're doing TF minus 50, since we know that the final temperature is actually larger than 50, right? So we want to make this positive, so we write it 40 times TF minus 50. Heat gained by the water is 400 times TF minus 50. And then the heat lost by the aluminum is going to be 258, 90 minus TF. Right? Then we can combine these. We can say 328.4 plus 4 TF plus 440 TF minus 50 is equal to, and then multiply that. So we get 23,220 minus 258 TF, right? And then we can multiply this in, 328.4 plus 8 to that side, minus 328.4, and then you get 702 TF is equal to, and then this one gives you 44,891.6. The final temperature comes out to be equal to 63.95 Celsius. So that proves one thing here. That means initially our guess can be anything. We can guess that the final temperature is greater than 50. We can guess that the final temperature is below 50. Our guess is not detrimental to us, and it doesn't take us down the wrong path. Both ways gives you the same answer. As long as you set it up correctly and take the absolute value, you can guess that the beaker and the water and the ice are all gaining heat, or you can guess that the beaker and the water and the aluminum is losing heat, right? You can put these on the opposite side, and then you can put the heat gained by the ice on the left side, right? And then you will still get the same final temperature. The final temperature will be 63.95 in either case, right? So this is a good example of what's known as a calorimetry problem. Taking objects at different temperatures, mixing them together, and seeing what the final temperature of the system will be, okay? So this is a good example of that. Thank you very much.